In the next few slides, I will give you an overview of the plan space planning algorithm PSP. This will be a generic version of the algorithm, and I'll follow this with some implementation detail that will make things more specific. So here's a quick recap of the search problem as we've defined it so far. We are given the statement of a planning problem consisting of a set of operators, an initial state, and a goal condition. Then we need to define a search problem, which consists of an initial state, and our initial state was the empty plan, which isn't quite empty. It consists of the init action and the goal action. These were the two dummy actions we've introduced to encode our initial state and the goal condition into the plan. And then we have one ordering constraint, namely that the init dummy action must come before the goal dummy action, and we have no variable bindings and no causal links initially. The goal test, as we have just seen, is simply to check whether a plan has flaws. If it has no flaws, then our plan is a solution state. What I haven't mentioned so far is the path cost function. That's simply because the path cost function is not very relevant here. You can choose pretty much anything you like, for example, the length of the plan as usual. Note that this path cost function would not be related to the cost of the plan refinement operations, but to the cost of the plan that we're searching for. And the final component of our search problem is the successor function. And here we will consider all those refinements of our current plan that maintain the ordering and the binding constraints in a consistent fashion. So our successor function will allow the application of more than one plan refinement operation at a time. And here is an informal overview of the basic operations that we need to perform during our plan space search. The basic idea, the main principle behind the algorithm is that we always refine our partial plan while maintaining the ordering and binding constraint in a consistent fashion until the plan has no more flaws. In some sense, this is the main loop of our algorithm. Then, within this main loop, what we have to do is first find the flaws that are currently in our plan. So these flaws can be either sub-goals or threats. We need to identify them so that we can remove them from the plan. And we will deal with these flaws one at a time. So the next step is to select one of those flaws. Once we've selected a flaw, we need to find all those ways in which the flaw can be removed from our plan, in which it can be resolved. And again, we need to choose one of the resolvers for the selected flaw. And finally, we refine our plan according to the chosen resolver. So we've selected a flaw, we've chosen a way to get rid of this flaw, and now we apply this to our partial plan. This is the step that corresponds to a state transition in our search space. And of course, while we are refining our plan with our chosen resolver, we've got to make sure that we maintain our ordering and binding constraints. So these two are connected, and we need to make sure that our constraints are consistent. If our constraints are no longer consistent after we've applied a resolver, then this node is a dead end in our search space. And here is what I've just told you in pseudocode. We define the function PSP that takes a partial plan as input. The procedure then refines this plan into a solution plan. Note that there's no planning problem given as input. That is because initially the plan that is given to this procedure is the empty plan, which encodes the planning problem as it has the dummy steps init and goal, having the initial state and the goal. Then the first thing we do is we compute all the flaws that are currently in the plan. And there are two types of flaws, of course, namely the open goals, the preconditions that are currently unsatisfied, and the threats that exist within the current plan. And if this set of flaws is empty, that means we have reached a solution plan, because, as I've told you before, no flaws means a solution. But if there were flaws left in the plan, then we can now choose a flaw, which is the flaw we want to remove from the plan next. And once we have selected one of the flaws, we can compute all possible resolvers for this flaw in the current plan. If the set of resolvers is empty, that means there's no way to remove this flaw from the plan, and that means we can return failure, because this partial plan can never be refined into a solution plan. But if there were resolvers in the set, then we have to choose one to remove the flaw from our plan. The next step then is to generate a new plan, which consists of applying the resolver to our current plan. This is the step that generates a new search node in our search space. And this time I haven't defined the search procedure as an iterative procedure, but as a recursive procedure where the recursive call comes here. So we've generated a new node and we simply apply the PSP procedure to that new node. Now, there are a few things to say about this algorithm. Firstly, it contains a number of functions that I still have to define. For example, how to compute the open goals in a plan, or how to find the threads that exist in a given plan. Also, I need to be able to compute the resolvers that are available for a given flaw in the plan, and I need to define how I can apply these resolvers to a current plan. These are implementation details that I will look at in the next section. But before I get here, there are two more functions that look quite trivial but are actually different. As you can see, I've chosen different names for this. Firstly, we need to select a flaw, and secondly, we need to choose a resolver. And there's a good reason why I've chosen two different words for these two different functions. The two functions choose one and select one represent choice points in our algorithm. Let me first describe the choice point where we select a resolver. So we have a function called resolvers choose one that selects one of the resolvers for our chosen flaw. This is a non-deterministic choice point. So the way the algorithm is described is as a non-deterministic algorithm, which means we need to turn this into a deterministic algorithm for the implementation. And this choice point is one that we need to backtrack over. That means it's a non-deterministic choice point. We need to come back here if we fail in one branch and try a different branch in our search. The other choice point, where we select one of the flaws that we try to resolve next, is a deterministic selection. That means we don't need to backtrack over this choice. That means we can choose one of the available options and then don't need to explore the other options at this point. And the reason for this is very simple. If a plan contains multiple flaws, we need to resolve all these flaws before it becomes a solution plan. But the order in which we do this is not important. Since flaws don't usually interfere with each other, we can deal with one flaw after another, and whichever flaw we choose first does not prevent another flaw from being resolved. So the order in which we choose the flaws is not important, at least not for completeness. Our algorithm will still work in whichever order we choose the flaws. But of course, the order is very important for the efficiency of our planning algorithm. For example, consider a plan that has one flaw for which we have no resolver and several flaws for which we have resolvers. If we first choose those flaws that we can resolve and then deal with the flaw that has no resolvers last, we create a search tree that has no solution nodes, of course. Whereas if we first choose the one that has no resolvers, we immediately terminate our search. So, important. Flaw selection is a deterministic selection, and we don't need to backtrack over this selection in our implementation. Selecting a resolver is a non-deterministic choice, and we need to implement this as a backtrack point.